So equation one cannot be satisfied. So how it is satisfied? This can be satisfied. So we made an error, and what is that error? B can be invariant अगर या तो अल्फा सिफर हो और या बीटा सिफर हो यानी दूसरे लफ्जों में the probability that the symmetric state would be occupied and the probability with antisymmetric state would be occupied, so either one can be occupied, sir, for one type of particle. So if the particles are fermions or one type of particles, then one of the probability would be non-zero, probability amplitude would be non-zero, and if the other particle, we talk about other particles, say for example boson, then the probability amplitude for that type of state would be non-zero and the other one would be zero. So this is a universal fact, by the way. It can be considered as a universal fact. Why? Because there are only just two types of particles in our universe. One of them are bosons and the other ones are fermions. So the probability of occupation for the symmetric anti-symmetric state would be sort of disjoint. That is, both cannot be true for one type of particle. Yeah. So both can be true. That is, they have equal probability, जैसे हमने equation number one में कहा है. But both cannot be true for one type of particle. One type of particle could be in one type of state, and the other type of particle would be in the other type of state. So we can say, uh, so, uh, but uh, an error is made, i.e., P can be P can be invariant if alpha is equals to zero or beta is equals to zero. So here we talk about or, not and. Yeah. So the resolution क्या है? Resolution एक postulate है, एक fact है, universal fact है, जिसको symmetrization postulate कहते हैं. तो we say, so the resolution of this discrepancy mm, might be related, might be related to, might be um, or might be stated in terms of, stated as the symmetrization postulate. Symmetrization postulate. Yeah. So it is basically a universal sort of fact about those type of particles. And what is the postulate? So we let's give you the statement, the allowed. So remember हमने start किया था allowed dynamical state से. So the allowed dynamical state of two particle system. Let's say अभी हम बात कर रहे हैं uh, particle two particles are either all symmetrical, all symmetrical का मतलब है alpha is equals to 0 and beta is not equals to 0. Yeah. Or all antisymmetrical. इसका मतलब है कि alpha is not 0 but beta is equals to 0 under, and what is the condition? Under interchange of particles. So this is the symmetrization postulate. So हमने दोनों बातें कर ली, एंटी एक्सचेंज डिजेनरेसी भी और सिमेट्राइजेशन ना। यहाँ पर एक चीज का ख्याल रखना है कि यहाँ पर जो हम इस्तेमाल कर रहे हैं वर्ड ऑल, uh, there was nothing in the mathematics, यानी अगर फर्ज करें हम यहाँ पर वर्ड ऑल इस्तेमाल कर रहे हैं एज सम सॉर्ट ऑफ अ क्वालिटेटिव डिस्क्रिप्शन of this fact, universal fact. So one cannot say anything from the mathematics. हम इसको क्वांटिफाई नहीं कर सकते, इस फैक्ट को हम क्वांटिफाई नहीं कर सकते, जो हम यहाँ पर एक यूनिवर्सल फैक्ट डिफाइन कर रहे हैं. It is basically some sort of a truth of nature. Yeah, that is, there are two types of particles, and those types of particles would uh, would would occupy states which are either symmetrical or antisymmetrical depending upon the number of particles. So this is a very important fact, that the word all makes it a postulate. And when we say all makes it a postulate, so postulate is something which is some sort of a truth of nature. Uh, and since it is a truth of nature, so you cannot justify it from mathematics. Yeah. So let me emphasize on this point. Note एक लिख लेते हैं. The So we have explicitly added the word or used the word all in the statement of symmetrization postulate. So the addition of the word all, what does it do? It makes it a postulate. And why is that? There was nothing in the mathematics, by the way. In the mathematics, to say that, say, electrons, क्योंकि let's say electrons are one type of particles, बुनियादी तौर पर electrons are fermions, for example, could not be sometimes in symmetrical state, and times in antisymmetrical state. समझ में आए समझ में आया ना आपको कि इसका मतलब है एंटीसिमेट्रिकल स्टेट्स, इसका मतलब है states. Yeah. So, in fact, we postulate that any type of particle always shows one kind of symmetry, not both kind of symmetry. Either it shows the symmetry or it shows the antisymmetry. It cannot show that any type of particle cannot show both type of symmetries. Yeah. So, and जब मैंने आपसे कहा था न्यूक्लियाई के लिए, so nuclei is a particle. Yeah. And that particle, nuclei is a composite particle which is basically made up of protons and neutrons. So हम बात यहाँ पर फंडामेंटल प्रॉपर्टीज की बात कर रहे हैं, ट्रूथ ऑफ नेचर की बात कर रहे हैं. सो वी कैन से वी पॉस्टुलेट, यानी जब भी हमें पॉस्टुलेट लिखना पड़ गया, in fact, rather than some mathematical argument or some mathematical conclusion. So उसकी जगह पर हमें postulate लिख रहे हैं. So we postulate that any type of particle, either it is in fact a fermion or boson, always shows one kind of symmetry, one kind of symmetry. Either the state would be antisymmetric or symmetric. It is left to the then uh, one can think about. So it is left to the experimentalist to determine which kind of particle applies to which kind of symmetry. Yeah. So then one perform experiment. So it one would say it is left to the experimentation experiment to sort of determine uh, the the kind of symmetry for a particle. I mean, which for a specific type of particle. ठीक है? Okay, so this is basically for two particles. Uh, then we can go on for we can apply this postulate to any number of particles. So let's say there are n particles. So we started with two particles. Now we can think about a system with n particles under any permutation of particles. The symmetry of all state is either symmetric or antisymmetric. So one could say uh, the symmetrization postulate is valid for any number of particles, not just two. So for a system with n particles under any permutation of particles, of the particles, of the particles, the symmetry of all states is either symmetric or antisymmetric. Symmetric. Yeah. So and this is basically valid for so one can then define such a state. So given n particles, let's say to be placed into a certain state, into a certain certain set of into a certain state or set of orbitals. So we have, let's say, uh, for example, we have We define those orbitals as q alpha, q beta. So here q represents the particles, and alpha beta they sort of define orbitals or designate orbitals. Q, gamma, etc. Uh, so and then we can write the tensor product, whose tensor product वो कैसे लिखी जा सकती है? So one can write the orbital as q alpha, q beta, q gamma, and so on. This state can be written as the tensor product of q alpha, of q beta, of gamma, so on. So this is basically written. And so uh, you could also write in another way, or or you could also write it as q alpha 1. So इसका मतलब है alpha is the orbital and 1 is the particle number 1. So that is alpha is beta is an orbital and 2 is the particle number 2. Gamma is the orbital and 3 is the particle number 3, and so on. इसका मतलब है to indicate which particle in in which orbital. That is, particle number 1 is in orbital alpha, particle number 2 is in orbital beta, particle number 3 is in orbital gamma, and so on. Then the only interesting and sort of useful multi-particle states are two. That is the one which is fully symmetric and the one which is fully antisymmetric. Yeah. And so जैसे कि हम सिमेट्राइजेशन postulate में कह चुके हैं. And then the only sort of interesting and sort of useful multi-particle states are of two types. Number one, कौन सा? The fully symmetric state. दैट इज फुली सिमेट्रिक स्टेट का मतलब है कि जितने भी पार्टिकल्स हैं अगर हम उनको इंटरचेंज करें तो वेव फंक्शन ऑफ दैट स्टेट वुड नॉट चेंज, सो दैट वुड बी नोन एज द फुली सिमेट्रिक स्टेट. या एंड द other is fully anti-symmetric symmetric state, मीनिंग कि उस स्टेट में, मल्टी पार्टिकल स्टेट में, अगर किसी भी पार्टिकल को किसी भी पार्टिकल से इंटरचेंज किया जाएगा तो साइन ऑफ द स्टेट वुड चेंज. एंड सो दिस कैन बी this can be uh, can be can be formed, rather can be formed by applying a projector or an operator जिसको हम projection operator कह रहे हैं. So there are only symmetric state. fully symmetric state को हम let's say S से जाहिर करते हैं, और fully symmetric state वी हैव अ नॉर्मलाइजेशन कांस्टेंट n फैक्टोरियल, जैसे हमने वहां पर √2 लिखा था, रिमेंबर। एंड एनी परमुटेशन जो है वो इज पॉसिबल अगर मैं इंटरचेंज करूंगा p फॉर द परमुटेशन। सो अगर मैं चेंज करूंगा, द साइन ऑफ द वेव फंक्शन वुड नॉट चेंज। और दूसरा क्या हो जाएगा, दूसरी स्टेट को हम कैपिटल ए से जाहिर करें, एंड दिस इज बेसिकली अगेन the n factorial, which is the normalization constant, plus p, and then we write minus 1 to the power p. So to the power p, number of permutations, कितने exchanges हैं, yeah, times p is the permutation. So यहाँ पर we are summing over the n factorial possible number of permutations. So यहाँ पर जो ये आ रहा है, ये बेसिकली आ रहा है ये या या इनफैक्ट जो दूसरी ए के अंदर भी, तो दोनों के अंदर बुनियादी तौर पर बात हो रही है। तो हम इसको इस तरह से ना लिखें, अगर दोनों का कहें, सो वी कैन राइट दैट इज sum sum over the n factorial possible possible particle permutations permutations। और ये जो -1 to the power p आ रहा है, that is basically the parity of the of a permutation equal to the number of pair interchanges। So this uh, -1 to the power p जो है वो क्या है, parity of a permutation of a permutation, and this is basically equal to the number of to the number of pair interchanges, pair interchanges, that is, you interchange how many number of pairs of interchanges have been performed, yeah, and that would lead to the sign of the wave functions, yeah। So we would have sort of an alternate sign आ रहे होंगे अगर हम मोर देन वन पार्टिकल करें। एंड ये जो आपने इक्वेशंस लिखी हैं ये काफ़ी मुश्किल हैं, सो फिर हम इसको एक डिटर्मिनेंट की सूरत में लिखा जा सकता है। सो फर्मियंस के लिए फुली एंटीसिमेट्रिक, सो सो फॉर fermions with fully antisymmetric with fully antisymmetric मल्टी पार्टिकल स्टेट्स क्या हो जाएंगी, मल्टी पार्टिकल स्टेट्स। द स्टेट वेक्टर कैसे लिखा जा सकता है, द स्टेट वेक्टर वेक्टर फॉर fermions with fully antisymmetric multi-particle states, वो कैसे लिख सकते हैं, we can write it as which is equals to 1 upon under root n factorial, the determinant would be u alpha 1 u beta 2 so on q gamma 3, so on up till, sorry, no, we have to write it, no, this is wrong. So we have to write it. So these are all alphas, by the way. Why? Because we have different rows. So this is an alpha row. So, so this is alpha, this is alpha, and so on up till Q alpha M. And then we would have for beta, Q beta 1, Q beta 2, Q beta 3, so on up till Q beta nth particle. And then we go all the way down to Q gamma, gamma 1, Q gamma 2, Q gamma 3. Gamma, alpha, beta, gamma are the orbitals. Q gamma nth and determined close. Okay. So ये किस चीज के लिए? This forms orbitals alpha, beta, gamma, and so on. And using some sort of a determinant जिसको आप क्या नाम देते हैं? Slater determinant here. So if you remember, formed from the orbitals alpha, beta, gamma, so on, using the Slater determinant. Yeah. एंड यहाँ से आप पॉली एक्सक्लूजन प्रिंसिपल बना सकते हैं, मीनिंग इफ टू particles were placed in the same orbital, for example alpha is equals to beta, टू रोज जो है वो कैसी हो जाएंगी? सेम हो जाएंगी। और अगर टू रोज सेम हो जाएंगी तो वेव फंक्शन जो है वो सिफर हो जाएगा, मीनिंग इट इज प्रोहिबिटेड, यानी हम डाल नहीं सकते दो पार्टिकल्स को एक ही स्टेट के अंदर, विच इज बेसिकली नोन एज द पॉली एक्सक्लूजन प्रिंसिपल। सो इफ किधर गया कर्सर? if two particles were placed in the same state, in the same orbital rather, orbital, i.e. अल्फा इज इक्वल्स टू बीटा हो गया अगर टू रोज क्या हो जाएंगी? सेम, टू रोज would be same. And you know from for the properties of the determinant, then जो वो है आपका ऑर्बिटल सिफर हो जाए, सॉरी वेव फंक्शन सिफर हो जाएगा। सो देन साई जो है वो क्या होगा? जीरो हो जाएगा, जो हमारा वेव फंक्शन है सिफर हो जाएगा। ठीक है ना? मीनिंग इसका क्या मतलब है? दिस implies it's prohibited uh, to place two fermions in same orbital, which is the Pauli exclusion principle. And so this is Pauli exclusion principle. And what is Pauli exclusion principle? Two fermions, two fermions cannot cannot occupy the same individual quantum state. Yeah, which is uh, which is basically the Pauli exclusion principle. And so, in fact, the end states which we have used in this slated determinant above must all be different. Yeah. So, which says that the n states must all be different. Must all be different for fermions. Now, for similarly for bosons के लिए भी हम कर सकते हैं. Actually, जब इसका जो for bosons, uh, one needs fully antisymmetric, sorry, fully symmetric, symmetric multi-particle states. The state vector would be invariant under any particle permutation or particle interchanges. So this is basically the property for boson. So the state vector is is invariant under any permutation, under any permutation or or pair interchanges or pair inter interchanges. So one can use a similar, in fact, sort of a determinant that is a slater determinant with a slight modification कि उस determinant के बिल्कुल corner पर हम plus sign लगा देंगे suggesting that it is for slater, it is for boson. So um, a similar representation, a similar representation can be made with a slight with a slight modification to Slater determinant. कैसे? So we would have a state psi and we would have 1 upon under root n factorial. Then we would have a core normalization factor, which is small n1 factorial, small n1 factorial, and 2 factorial, and so on up till n, rather nx and x factorial in x factorial, and then we have again उसी तरह से you would have alpha 1, alpha 2, so on up till q alpha n, और then you would have उसी तरह से q nu 1, q gamma or nu whatever, nu 2, so on up till q nu n, and then we have this, और यहाँ पर हम एक प्लस साइन लगा दें। प्लस साइन जो है वो किसको यूज कर रहा है? साइन ऑफ ऑल टर्म, जितनी भी टर्म्स इसको एक्सपेंशन पर आएंगी सबके सब पॉजिटिव होंगी। यहाँ n1 जो है, n1 बता रहा है इन स्टेट नंबर ऑफ पार्टिकल्स इन स्टेट 1, नंबर इन फर्स्ट स्टेट, n2 बता रहा है नंबर इन सेकेंड स्टेट, and so on. Yeah, so this is basically for correct normalization. This is for correct normalization. That is स्टेट 1 के अंदर पार्टिकल्स की तादाद स्मॉल n1 है, स्टेट 2 के अंदर पार्टिकल्स की तादाद स्मॉल n2 and so on. So this is basically some sort of a correction to the normalization. So in fact we have still 3 minutes. So एक एग्जाम्पल के तौर पर हम क्या, फॉर एग्जाम्पल द फार्मूला इज जो हमने ऊपर लिखा है, इट इज समवॉट कॉम्प्लिकेटेड। सो अगर मैं इसको 3 पार्टिकल्स के लिए लिखूं, तो लेट्स से एग्जाम्पल के तौर पर so let's say we have an example. So consider a system of 3 particles. Yeah, and let's say we talk about bosons, these 3 particles. So 3 particles, or let's say हम इसको specific कर लें bosons. So let's say 2 are in state alpha, and 1 in state beta. Then जो वेक्टर होगा हमारा वो क्या होगा? इज इक्वल्स टू 1/√3 फैक्टोरियल, क्योंकि 3 पार्टिकल्स हैं, और 1/√, आपके पास क्या होगा? 2 फैक्टोरियल एंड 1 फैक्टोरियल, बिकॉज एक में 2 और फिर जो स्टेट्स बनेंगी वो क्या होंगी? अल्फा के अंदर पहला पार्टिकल, बीटा, अल्फा के अंदर दूसरा पार्टिकल, बीटा के अंदर तीसरा पार्टिकल, या क्या हो सकता है? अल्फा के अंदर दूसरा पार्टिकल, अल्फा के अंदर पहला पार्टिकल, और बीटा के अंदर तीसरा पार्टिकल, या अल्फा के अंदर पहला पार्टिकल, तीसरा पार्टिकल अल्फा के अंदर और बीटा के अंदर सेकंड पार्टिकल, या इनका इंटरचेंज, अल्फा के अंदर तीसरा पार्टिकल, अल्फा के अंदर पहला पार्टिकल और बीटा के अंदर दूसरा पार्टिकल, या प्लस अल्फा 2, अल्फा 3, बीटा 1, प्लस अल्फा 3, अल्फा 2, beta 1. So these are the combination. So this is equivalent. This is